Ladies and gentlemen, and children of all ages, welcome to the Docgizmo Science Theater. It's my great pleasure to introduce to you the master of discrepant event science, the presenter of unexpected but unexplainable scientific oddities. This gentleman and his dedicated and talented wife have spent years bringing together a marvelous array of the finest science demonstrations available to the modern world. Many would say that he performs magic, but all magic is science, and science is his stage. Phil Arnold comes direct from Ashland, Kansas to share with you his excitement and love of science. Please welcome the man known to thousands as Docgizmo.
I'm Docgizmo. I got that name because I gave it to myself, because I build gizmos. And I build gizmos because my wife teaches chemistry and physics and math and physical science and a bunch of other things in a little high school out in western Kansas. Enrollment of about 125 in high school. And I expect some of your classes are bigger than that. Anyway, I'm an old rancher, and she's a fine teacher, and she'd come home from a conference and say, I saw the neatest demonstration, and I know the school's not going to buy the equipment. Could you build it for me? And I said, sure, I can do that. So I started building things, and it's gizmos. What's a gizmo? Anybody know what's your definition of a gizmo? Something you build to do something. That's a pretty good definition. Anybody else? A doohickey. I hear that. Thingamabob, all kinds of things. Well, I'm a gizmo. Docgizmo. And my definition is a gizmo is a thing that's made out of stuff that does something. And I'm a thing, I'm made out of stuff, and I do something. I do discrepant event science. And all through history, we've had scientists like you and I. And I hope you're scientists, because again, my definition of a scientist is somebody that looks around themselves and says, I don't understand. Because that's what science is all about, trying to understand all of the things that are going on in this world. And over the centuries, we've learned a lot of things. And the more we learn, the more we find out we don't know. Every time we open a new door, there's a whole new world out there that have questions and answers. You need to have your minds open to be able to come up with some of the answers that we still don't have. And if you go back into history, you find that the scientists didn't have all the technology that we have now. They didn't have all the internet and computers and all of the stuff that we use. And if you go back far enough, they didn't even have books. They had to use their mind. This marvelous computer you keep between your ears, and they would look at something and say, you know, I don't understand that, but I think I can figure it out. I'm going to make a guess. And in scientific terms, that guess is called a hypothesis. So they would form a hypothesis of how they thought something worked, and then they'd do an experiment to see if it worked. And if it worked, that was great. They had the answer. If it didn't work, they found out that they learned a lot more from their mistakes than they do from the good things. The things that work, you just keep doing them over and over and over. You're never motivated to do any better. When you make a mistake, you got to say, hey, that didn't work. What do I do to make this work, to get better? So use your mistakes. Don't be afraid of them. Use them. Take advantage of your mistakes so that you don't do it again, and you get better as you go along. Now then, I have here a model of the scientific method. Scientific method, I call it a think tube. And it's just a piece of PVC pipe that has some strings running through it. And much of science is like this. You can't tell what's going on because it happens at a molecular level or some way you can't see. You see what happens, but you don't know why. So watch what's going on here, and you see that when I pull this pom-pom, these two are hooked together on that string. And you say, okay, that looks pretty simple. I can figure that out. Down here at this end, it works the same way. And so now I hope you've formed a hypothesis, a guess of what's going on here. Now we do an experiment to see if we can duplicate what we did. If I pull this one, what happens? Two long ones, two short ones. It came this way, didn't it? But we know it's hooked up here. And so now you say, well, it's doing things that I don't understand. And you've got to form a new hypothesis, because this is hooked up here. It's also hooked up this direction. It will come back come back this direction, still hooked up here, does anything I want it to do. And I'm not going to tell you how it works because it's a think tube. You got to think about it. Use your mind. Innovate. Say, I can figure that out. And it's really pretty simple. Now then, I have some green stuff here that's sitting here on the fire boiling, and as scientists you'd say, well, I don't know what that is, it's green stuff. And I'm telling you that it's water, and we all understand that if you take water and put it in a container and put fire under it, it's going to boil eventually. We boil eggs and spaghetti and all kinds of things when we're cooking. So, if you put heat under a container to make it boil, can you make it boil by putting ice up on top of it? Well, this is one of the discrepant events that I do. It's, get things turned around here so I don't burn up the, I've got a baggie of ice. And if I take this ice and put it up on top of this container, it starts boiling again. Boiling water with ice. And you say, well, that doesn't make any sense, but it makes perfect sense. This is good science. And I'll tell you how this works. When this was sitting there on the fire and boiling, you said, well, it's green stuff boiling. What was above the green stuff? Anybody? Air. How many say air? Well, everybody's got their hand ups wrong because there isn't any air here. This is all water. Liquid water, water vapor. When you put heat under water, those little molecules of water start getting excited, start picking up energy and start bouncing around. And they get bouncing and so energetic that they take up 1,200 times as much room as a molecule of water vapor as it does if it's a molecule of water liquid. And when you put this ice up on top here, it had pushed all the air out. This is all water, liquid water, water vapor. You put ice up on top here and it starts condensing those vapor molecules back down, which means there's 1,199 places up here where there isn't anything. So we have a vacuum in here. And because of that vacuum, this water boils at a lot lower temperature. And if I get around and have enough time, we'll get back and I can hold this in my bare hand and we can get it to boil again. Boiling water with ice. I kind of like fire. Kids like fire, I like fire. It's an important part of our environment. It's around us all the time. And we need to know what it can do. We don't need to be afraid of it. If we're not careful with it, it can cause damage. But I kind of like fire, and here's a little demonstration that has some fire. I have this container, this water jug, and I poured some alcohol into it a little bit ago. And I'm going to roll it around there a little bit, and then I'm going to pour it all back out, and I'm going to, excuse me for moving around on you here, I'm going to dump this alcohol out so that there isn't anything left in there. I don't want a bunch of liquid in this container. But we dump all that back out of there. So now all we have is alcohol vapor and air. And I call this my whoosh bottle. Now then, I dumped everything out of it, but now there's something back in there. There's water there. As this alcohol burned, it combined hydrogen in the alcohol, oxygen in the air, and formed water. So now we've got water back in here, and if I turn this up, you can see that water running dripping out of the container. And that's water that we formed as we oxidized the alcohol. Here are a couple of rusty iron balls. If you take iron and put it out in the open, it's going to do what? Rust. It's going to combine with the oxygen in the air to form rust. One of these balls has aluminum foil wrapped around it. Just big old heavy rusty iron balls. But aluminum is more reactive than iron. And so I can actually pull the oxygen out of the rust. That's called reduction. If you take oxygen out of something, it's reduction. If you add it to it, it's oxidation. So we reduce the iron back to the rust back to iron. We use the oxygen to produce aluminum dioxide. And just like this fire here, it's exothermic. It gives off heat. And it gives it off like this. That's oxidation reduction, done right here in my bare hands. And that's also chemistry. Chemistry is all around us. And I hear people say, we got to get rid of all these chemicals. They're terrible. They're polluting our world. Well, some of them are, but you and I are chemistry. We're a marvelous chem lab. We're doing all kinds of things. I read the other day where there's 30,000 chemical reactions going on in your head all the time. We breathe in oxygen. It combines with the carbon in the food we eat, and it generates heat. Exothermic, that's what keeps us alive and functioning. It's chemistry. And chemistry is just the study of how all the elements work together to combine and to form all the things that we feel and touch and around us. Don't be afraid of chemistry. Enjoy it. Sometimes it's kind of explosive. As I said, I kind of like to play with fire, and I have here a tuna fish can that I took a long, narrow strip of corrugated cardboard, rolled it up, put it in the can, poured some paraffin down over that, so now I've got a great big candle, and it provides me with a way to have a controlled fire when I need it, and I use my little torch here to light my candle, and I've got a can full of fire. And if I've got it here on a turntable, if I spin that turntable, what's going to happen? It's what? It might go out. Well, let's do the experiment. Well, we didn't exclude the oxygen. It just went round and round. That's what you'd really expect. Well, I have here a cylinder of wire. Just some screen wire attached to a bunny blue ice cream lid with a hole in it so that it will fit down over here. And if I set that down over there and now spin it, what do you think is going to happen? Well, let's do the experiment and see. Well, it jumped right up there, didn't it? Didn't go out, it got bigger. Now, I don't know whether you know what's going on here, but here again I'll tell you, and not take a lot of time. Air has mass. It has weight. And as this spins around, this screen wire grabs a hold of that air and starts it spinning. And what happens when you spin something around and around? If you tie a rock on the end of a string, where does it want to go? It wants to get away, doesn't it? Fly away. Same thing happens here. This air is being thrown out of here, which means down the middle of this we have a low pressure area. We have less air in the middle of this because it's being pushed out, being thrown out. And so this is a demonstration of weather. We have high pressure areas and low pressure areas caused by spinning masses of air that are hot or cold, and the air goes up or comes down. And so this is a demonstration of a fire vortex, a tornado, of weather of different kinds. Now, in order to have fire, what do you have to have? Three things. One of them. Fuel. You got to have something to burn. Oxygen. You got to have oxygen, something for the fuel to combine with. What's the third thing? Heat. Yeah, you guys are sharp this morning. You got to have those three, and if you take away any one of them, the fire goes out. If you take away the oxygen, the fire goes out. I can take the oxygen away by putting this container down over it. The oxygen's excluded. Fuel still coming up here. Still have vaporized fuel, the paraffin. You saw the smoke. Take the oxygen away, relight the smoke there. Fire goes right back down in there, follows in. To take the fuel away, can't very well do it there, but I can turn the valve off here to turn the fire off. If you got a fire that you don't want, do the easy way. Take away the fuel, take away the oxygen, or take away the heat. And to take away the heat, firemen a lot of times use a fine mist of water, because those little tiny droplets of water will absorb so much heat as they turn to steam that it will take whatever's burning below its kindling temperature and the fire goes out. I don't use water, I use the screen wire, because it has so much surface area that it will absorb the heat, not going to exclude the oxygen because it can go right through here, not taking the fuel away, just taking the heat away, and the fire goes right out. Okay? My wife teaches chemistry and physics in high school, and she sent her high school chemistry book along with me. And she said, Phil, you know, if you would just read this book, maybe you'd get smart enough to be able to talk to people about chemistry. And I said, well, it's a pretty big book. I don't know whether I can carry that around with me or not, but I do. And right here in front, there is a chapter here on oxidation, and it says if you have heat and fuel and air, it demonstrates rapid oxidation right here in the textbook. And I don't know how many of you have textbooks that demonstrate what it's teaching, but this one does. And if I take the oxygen away, the fire goes out, and I'm back to having a textbook that I can read and maybe learn something from. When I was introduced there, the introduction said that I don't do magic, that all magic is science. And the one thing that I do that would kind of look like magic is this thing, which is 110 line coming in here. It comes, one side of it comes through this blue switch up to this blue bulb, across to this red socket and bulb, back down to this switch. And in order to have a closed circuit, a circuit that something works, it's got to go clear around. Alternating circuit electricity has to go back to where it came from to have a circuit. So if I turn on the blue switch, I would expect nothing to happen because the red switch is off. I haven't completed the circuit. If I turn on the red switch, it should turn, well, no, it didn't do anything, did it? Maybe the electricity can't run up this line. Could it be that's possible? Huh? No, don't believe that. That's not true. Electricity runs up and down lines. But I'm going to turn it over, and it turns on. Well, maybe there's, well, no, it works both ways. Well, if I turn the blue switch off, it ought to break the circuit and turn everything off. But it just turns off the blue bulb. And the red switch just works on the red bulb. Now, something's not working like it should because you can see the wires in here, and it's got to go. So let's do something else. Let's take the blue bulb out of the blue socket with the blue switch and the red bulb out of the red socket and put it over here in the blue socket with the blue switch, and the blue bulb in the red socket with the red switch. And now the blue switch should take care of the red bulb. No, it takes care, still taking care of the blue bulb. And the red switch is still working on the red bulb. Now this isn't magic. This is technology. We now have things that are called diodes. And diodes just let electricity run through one direction. And alternating current goes both directions. It goes back and forth. And so diodes in here just allow the electricity to come through the red switch and the red bulb when it's going one direction. When it turns around and goes the other direction, it just goes through the blue switch and the blue bulb. So this is technology, not magic. Let's see here. I have here a container of chain, beads, and this whole container is one big long string of beads. And it's a model of a polymer. And you're all wearing polymers. Chemists now are making all kinds of artificial things that just string things out. You just keep adding new elements to the end of a string of a polymer. Unlike water, which has 2 atoms of hydrogen and 1 of oxygen, and that's all you get. Polymers just keep stringing it out, and everything in this flask here is hooked together. It's one big long chain. And when I saw this, the demonstration was that this is a polymer, and if you start this polymer running from from one container to another, it will run back and forth just kind of like a siphon. And if you let it go long enough, it all runs out on the floor. And I thought, you know, that's kind of neat, but there's something else going on here that is more interesting to me. There was a scientist back in history named Newton, Sir Isaac Newton, and he dealt with motion. And Sir Isaac has 3 laws of motion, and the first one is that if a body is moving, it will continue to move in the same direction at the same speed until some other force acts upon it. That other force may speed it up, it may slow it down, it may change its direction. But it will continue to move at the same speed in the same direction. So in order for this chain to get out of this container, what direction does it have to go? Down. There's a bottom in this. It's got to go up because that's the open side. This chain's got to go up to get out of here. And if I start this up in that direction, it ought to go right to the ceiling and stick. That's what Sir Newton's first law says, right? But we know gravity's going to grab a hold of it and pull it back down, don't we? So if I start this up, as it picks up speed and momentum, it's still trying to climb to the ceiling. Watch what happens. You got about 7 seconds because this moves pretty fast. Still trying to climb to the ceiling. Sir Isaac Newton's law of motion. I got a banana here. How many of you like bananas? Oh, okay. How many of you peel the banana before you eat it? Okay. Those of you that don't like bananas, maybe you ought to try peeling it. They're a lot better when you take the peel off. Now, those of you that peel bananas,